Hey, and welcome to this short video about assembly programming for the Norsk Data ND-100 series of microcomputers. The prerequisite for this to work is that the ND-100 emulator and the ND-100 assembler is installed and configured. After installing Visual Studio Code, this IDE we are looking at, you need to install the ND-100 assembly plugin inside Visual Studio Code. This plugin gives you assembly language support, which includes syntax highlighting, Hoover information, code completion, and more. But the most important here is that it gives you the possibility to start the code, compile the code, start the code, and step through the code, as we will see later. In addition to this, we also have a documentation file, which is quite complete and gives you a lot of information about the CPU, the architecture, the instructions, and memory addressing modes. So, for example, we can look at, for example, CPU information and their registers. The registers. And here we see that we have the status register for user, 16 bits, the data register, and other registers, the name and their description. We do have, for example, instructions by, let's say, by category, and we can see there are different categories these instructions are categorized in. So if I want to see, for example, arithmetical and logical functions, click on that, and I see we have 1, 2, 3, 4, 5. And I can look at this ADD and click on that. I can see the format is ADD addressing mode and displacement, and it explains that add to the RA register the value in the memory address, the effective location. And we also have, for example, other categories that are interesting. For example, memory transfer instructions. So, for example, load instruction, where you load into A register, or load into T register, or load into X registers. Clicking on LDA, we can see the function here, where you have LDA, the addressing mode again, and then the displacement. We also have other more complex memory transfer operations that can transfer different things. We do have more description about addressing mode. Let me see, that was not the one, this one. That is showing how this is the variants there are of addressing modes, how the mnemonics are, and how you calculate the effective address for these functions. If we switch over to the source code for an Hello World in assembly for the ND-100, we can see that we have syntax highlighting by hovering over, by the coloring of the different copy is blue, which is a valid instruction. The DD register is shown as in another color because it's a valid register. Green for numbers, etc. If I hover over the instruction, you can see that it pops up this window with descriptions of the operand, the instruction and its operands. This is for all valid instructions. We also have this launch file, which is typical Visual Studio Code extra file that is needed to be set up correctly to make the Visual Studio Code able to start and debug programs. I will not go into details in this file right now, but it's necessary to to be able to start the compiled file. So if I look at the source code and I can put in a breakpoint, I push F9 for putting in a breakpoint. I can put in multiple breakpoints, but I'm gonna just need one. And then I push F5 to start the program. And actually I have to click this run and debug over here to show me information that is coming from the debugger. And we can see under this variables I have access to the CPU register values, and when I step you can see that it changes. For example, now I'm gonna load the T register to point to the hello string down here. After then you can see the T points to 13, which is probably the memory address of hello world. And to check that we can go to the T, and you see there comes up this little binary data over here. I can click that and it will read memory over here, and you can see the hello world text over here. And I can step through the code. I use F10 to step over. So here I'm going to step over. Well, if it's step over or step into right now, it doesn't really matter. But on this jump with a link register, if I push F10, I will, which is actually a jump down here, and using after skipping all of these lines and exit, it will just go to line 9 here. So I push F10 and it went to 9, but it actually executed all of these instructions. So for showing that, I can see that when I go to this line next time and I push 11, which is step into, it will go to the line 18 here. And to focusing again a little bit on the left side here, we can see that P points to 22, which is the memory address, actually not the line address here. So 18 here is the line address, but it's not the memory address. The effective address is 22 calculated. And we can open STS register and we can look at the different flags here in the, if that was necessary to have more detail, so we don't manually have to decode the bits here. When the stepping in the, you can also see here in the call stack that originally started from main, which is up here, +5, which was the last place. We can hold that number. So +5 is a 1, there's a 0, I guess, 1, 2, 3, 4, 5. So this was the place it was before it jumped. And now we are at unknown +0, which is a little bit odd. It should have shown push here, but it does show unknown. That might be a bug. I push F10 to step, and now it's unknown, and it does show 24. It should have shown reference to this one, but that I need to look into. And when I do, or at this point I can actually push Shift 11, F11, which means step out, meaning execute all instructions and until you exit the instruction. So I don't have to step through all of them. I could also put a breakpoint over here and push F5. That will be the same effect, but I can push Shift F11 and it will come up over there, even if I had didn't have a breakpoint. And you see with this or increase the DX register. DX is or the DX as the destination is 145. So if I push that, that should, no, sorry, destination X. I meant, yeah, it increased it to 2. And you can see that the next, now it should be 3. Yes, it's 3. To show the next functionality, yeah, I can also show that we do have more information from the CPU. We have these interrupt levels, which is showing the current program level, or interrupt level, the previous level, and since we don't have a program that is using interrupts, they are 0. We are running at 0 by default. There are 15 levels here, and it also shows the different configurations for ring, page table, and alternative page table, and the current P value, or the program counter, for this level. Typically, for example, at level 13 you have the real-time clock. At 10 and 12 you have interrupts from hard drives. No, for 11 I think it's hard drives. 10 is in from terminals, and 12 is out. I might be wrong, but there are different levels for different interrupts and different things when you're running, for example, Syntran have using almost all levels. In addition to the interrupt levels, you have internal registers. That is other registers that are not directly in the CPU. It's on the CPU board. It can be a 8-bit or probably a 16-bit flip-flop. That impacts system configuration depending on that. So this is the registers you read to get information. And you also have write registers, which kind of align with the read registers, but not always. So for example, the first one is panel controller, which is you write to, and then panel status, which is something you read back after you have written to panel controller. When you write to LMP, which is the lamps, which updates the LEDs on the original controller board, not controller board, but the panel controller, and which matches the read when you read from the OPR registers. But today is a register in Opcom, but I guess in the ND-10 they had these physical switches that will read the switches from the panel controller. We also have access to the memory management controller, and this is again linked to the current interrupt level, where we had page table 0 alternative page table 0. And since the code here doesn't use that, the page table that is set up is actually invalid or just 0. But in a case where you would have had MMS or memory management setup, this would show the actual configuration. And at the moment it actually shows the actual configuration, but it's all all 0. Yeah, so to finish this code, I can say I will set a breakpoint at this wait instruction. The wait instruction, when that executes on level 0 and no interrupts enable, it means it doesn't wait for an interrupt to happen, it just exits the program. So if I put F9 here and I push F5 and the program stopped, yeah, I guess it came to a wait instruction. So I can also see in what you don't see here, in the emulator console, that it wrote hello world on the console. So that was all about this controller or the debugger and the plugin. Thank you.